All right, hello, honor students for Unit 7. This is your super short mini lecture on uh, nuclear decay equations for beta and gamma radiation. Remember, everyone's required to understand the properties and be able to identify beta and gamma. You will just also be expected to be able to write. All right. So you're just going that one little extra half step. So remember when we talk about nuclear equations, we always have what we call a parent isotope, an unstable isotope, and a daughter isotope with some radioactive or high energy particle being released. So for alpha, we've studied it already really well. We always lose an alpha radiation, alpha decay. We always lose a helium-4 isotope. So on the other hand, we know that for beta decay, we always lose an electron essentially. Okay. And it can be written as two ways, an electron or a beta particle, right? You can reference it by its Greek symbol. All right. We know that beta decay is the second most dangerous alpha. If you had to choose a radiation to be exposed to, alpha would be better, beta was worse, and then gamma is just the worst of all because gamma is this high energy, okay, this high energy particle. Like it's just energy. There's no change in mass. There's no transformation of the unstable isotope. It's just immense energy being released. And gamma is often partnered with other types of radiation. It usually isn't standalone, but when it is standalone, gosh, you just have nothing but pure bad. Granted, I wouldn't say that having gamma and beta is also great, but how you would write these nuclear change equations is you start again with an unstable isotope. Remember, we're writing an isotope formation. So here, the whole number mass number goes on top, and then the identifying atomic number or proton count, right, goes on bottom for our notation. And what we would say is, let's take, for example, for beta, let's take carbon 14 with a proton count or atomic number identifying of 6 for carbon. When it undergoes beta decay, it will release one negligible mass electron, but with a charge of -1. And what that means is, according to keeping in line with the law of conservation of mass, you have to have the same amount of the subscript and superscript numbers before on the reactant side and on the product side. So what is 6 minus 1? What would we add to -1 to get to 6? Well, we would have the element with a mass of 14 and the element with a atomic number of 7. And that would be nitrogen 14 isotope would be produced, daughter isotope. So as you can probably tell, this is going to be super simple. And then as far as gamma, well, this is like the dream in terms of writing a nuclear equation, not, of course, receiving it or being exposed to it. But let's say you have uranium 235 isotope with an atomic number of 92. And for gamma decay, you literally just have energy, right? You just have this weird energy. So you still have 235 uranium 90 with an atomic number of 92, and that's it. So the biggest thing here is that you guys remember the particle and remember that the law of conservation of mass dictates everything. Okay, if your numbers aren't adding up before and after, you have a problem. So that's kind of all there. Congratulations. This is, I think, the shortest honors lecture ever. And I hope that as we enter our atomic assault project, that you guys enjoy becoming investigators and really applying your ability to identify and analyze the effects of nuclear radiation. So good job, you guys. Bye.